Look at that big slice of pizza. Man, that's a beautiful looking part of a circle, huh? Yeah, slice of pizza is basically a part of a circle. And if we found the area and circumference of circles, we can find the area and circumference of parts of circles. So let's get going because that pie is making me hungry. But that slice of pie is important because it represents a sector of a circle. So pause the video for a moment. Look at that picture on the left. What's a sector? So thanks for coming back. So a sector is an area. And it's the area that's between two radii and an arc of the circle. That's what a sector is. It's an area. It's a region. So if we want to find that area, a couple things you can do. One of the greatest things I've seen is going to Desmos.com, typing in that class code, and doing that activity called sector area. Seriously, give it a shot. It's one of the better things you'll do with your time. Come on back. I'll wait for you. Well, thanks for coming back. So what you probably learned there is how to find the area of a sector whose radius is some value r, and the central angle is theta. Okay, so that little symbol is called theta. It's a 0 with a little squiggly or a slash through it. Okay, I'll make mine that look like that. And we typically use theta as a variable to represent an angle. Okay, just like we use x for a variable in an equation or r for radius, theta represents an angle measure. So what you figured out was that the area of the sector of the circle is something out of 360. It's whatever that central angle's measure is out of 360 times the area of the circle, pi r squared. So because the sector is part of a circle, it's a fractional part of the circle. It's a part out of the whole 360. So that's how we find the area of the sector. So let's play area of a sector. Are you ready? Here we go. First example we'll do is to find the area of this shaded sector. If you want to pause it and do it, that would be great. All right, let's check your work. So your central angle is 45 degrees, so theta is 45. The radius is 20. So when I do my area, I'll do 45 out of 360 times pi times the radius squared. So doing a little bit of arithmetic, 45 out of 360 is 1 out of 8. So it's 1/8. 20 squared is 400. So my area is 1/8 of 400 times pi. Now, 1/8 of 400 is like dividing 400 by 8, which is like dividing 40 by 8. 40 divided by 8 is 5. So this area will be 50 pi. And let's see, it was centimeters, so we should say centimeters squared because area is always squared centimeters. Let's keep playing. Again, pause it if you want, give it a shot. So in this one here, we're given the area of the shaded region. So in my formula, area equals theta over 360 times pi r squared. I know my area is 14 pi. I'm looking for x, the value of the central angle. So I'm looking for theta. I'll call it an x, doesn't matter. I know that my radius is 6 centimeters. So this is another equation to solve. So let's start simplifying a couple things on the right side. So one thing you might notice is that 6 squared is 36. So if I do 36, and then if I divide that by 360, good things happen. Because 36 goes into 360 10 times. Do you also notice that the pi's cancel on both sides? So really the equation I have now is that 144 equals something divided by 10. Oh, I changed my 14 to 144. Sorry about that. So 14 is something divided by 10. When I multiply to undo that, I get x equals 140. So that's the measure of the central angle. It's 140 degrees. And it kind of looks that way too. All right, let's keep rocking and rolling. Let's talk about arc length. Now we're talking about the length of the arc. What we're talking about is this darkened area from A to B. I don't want to know the angle measure of it. I want to know is if I can pull this off, how long is it? So my answer is in a linear measurement like inches or centimeters or meters or feet or whatever the circle's dimensions are. So that's the length we want. And my question to you is, how is determining the length of an arc of a circle related to determining the area of a sector of a circle? So I'm thinking that the relationship is probably that they're both parts of a whole. So the arc length really is part of the circumference. So that's how we're going to deal with it. And remember, your circumference formula is 2 times pi times the radius. So the arc length is a fractional part of that. Let's play. So in this case, the radius of the circle is 24 centimeters. Angle BTA is 60. And I want the length of this arc here. I don't want the degrees of it. I know because it's an inscribed angle, the degree measure is 120 degrees. I know that. But that's not the answer I'm looking for. I want the length of it in centimeters. So what I'm going to do is I'm going to take my arc length, maybe we'll say like L for arc length, and it's the circumference. So it's 2 times pi times my radius, which is 24. But then it's a fractional part of it. It's 120 out of the whole 360. So here's why it's similar to arc length. Because it's part of the area. So 120 divided by 360 is 1/3. So it's 1/3 of 2 pi times 24. How about 1/3 of 24 is 8? So how about my answer being 16 pi? That the whole length of arc AB is 16 pi. And yeah, we'll throw our units down. 16 pi centimeters. Just like we did before, we can go the other way as well. Our last question that we'll do together. The length of arc ROT is 116 pi. Now, also because the minor arc RT is 120, I know that arc is 240 degrees. So what that tells me is that the arc length of 116 pi is 240 3/60ths of the circumference of the circle. So let's talk about solving that equation now. Well, 240 out of 360 is 2/3. This reduces down to 2/3. Notice that my pi's cancel. So if I want to solve this equation now, 3 times 116 is 348. 2 times 2 is 4. And if I do 348 divided by 4, my radius is 87. 87 what? 87 meters. 87 meters? This circle is gigantic. Holy cow. But more importantly, how did you do with circumference and area of a sector and arc length? Hope you had fun.